How's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to be talking about inertia, rotational inertia, what an object looks like when it's rolling versus what objects can look like when one of the objects is rotating and the other one is moving linearly. Okay, it's really just combining rotational motion and translational motion, or we say linear motion. How do we combine those things, right? We can look at something rolling, or we can look at a system that has a pulley and something moving linearly up and down, like an elevator, right? Okay, so let's start with the main idea now. I know we haven't talked about inertia up until this point, and it's kind of important because inertia is important with physics, right? But we're going to talk about it now. Cool. So, what is inertia? Basic inertia, not rotational inertia. Okay, but what is inertia, right? So it's simple, actually. First of all, it's just your mass. If we're talking about translational inertia, right? We just call that basic inertia. But what it is inertia is how easy or hard it is to get something moving linearly, okay? Or to stop it from moving linearly, okay? So how easy or hard it is to get it to start to move, and how easy or hard it is to stop it from moving, right? You're going to hear a lot of definitions for that, but I'm telling you, that's the best way to digest it. It helps you see everything, right? Because something with a very large inertia is going to be hard to start to move, and it's going to be very hard to stop moving, right? And we can see that something with very small inertia will be easy to start to move and be very easy to stop, okay? Now, rotational inertia works the exact same way. And again, regular inertia is just based off of mass, but rotational inertia somewhat defined the same way, but you know, it is a little bit different. So rotational inertia is, again, how easy or hard it is to do something, but in this case, it's rotating, right? So rotational inertia is based off how easy or hard it is to get something to start to spin, or how easy or hard it is to get something to stop spinning, okay? And again, you're going to hear a lot of definitions, but those are the best ways to eat it. Those definitions help you apply it to problems, apply it to conceptual questions, anything, okay, when we think of it this way. And just like with rotational inertia, okay, we see, just like with linear inertia, we can see something with rotational inertia where instead of just mass, right, the rotational inertia is based off of how far the mass is distributed from the axis of rotation, okay? So wherever the thing's spinning on, how far away, right, is the force being applied? Sometimes it's just the weight of the object, right? Sometimes it could be like pulling on it, right? How far away from the circle, or from the center of motion, or axis of rotation, sorry, how far from the axis of rotation is the mass distributed, all right? That's super, super, super important, okay? The further the mass is from the center of rotation, right, the further it is, right? Something like a disc, right? The smaller the inertia is, right? Where with the hoop, right? Something that hurt, like a hoop, right? Which is like the mass is distributed. Sorry, I think I said that backwards, right? Let's make sure we understand the objects we're talking about, right? So a hoop, right, is because right, it can be deceiving. So a hoop, right, is right. It's hollow in the center, right? Where a disc is all the way filled, right? It has mass all the way across. Where here, just for the axis rotation of a hoop, all the mass is out here, right? Because there's nothing in here, it's hollow. Where for a disc, there's mass all along there, okay? So, since a disc, the mass is closer to the axis of rotation, right? We're going to see how this beta plays in, and it gives it a smaller inertia versus a hoop, which has a much larger inertia. Okay, so what does that mean? It means that with, again, just like small and large, small inertias mean easy to move or rotate, right? Larger inertias mean harder to move or rotate, or harder to stop rotating or stop moving. Okay, I'm going to think of it both ways. So if a hoop has a larger inertia than a disc, that means a hoop is going to be harder to start to roll, right? And it's also going to be harder to stop rolling, okay? A disc is going to be easier, right? A disc versus a hoop. A disc is going to be easy to start to spin, right? But it's also going to be easier to stop spinning, okay? So those things are going to make sense as we start to work through here because we can prove those things, right? That's what we're kind of saying down here, but I'll get to that, okay? So, again, understand inertia, because if you understand what inertia is, you know these answers right away. You don't need to do any math because you can answer the conceptual questions. Now, if we ask you for values, you got to know how to do the math, right? But conceptually, you can be able to just answer these things because you know what inertia is, right? So again, inertia, just in general, right, is either how easy it is to get something to start to move or to start to spin, right? Or how easy it is to get something to stop moving or stop spinning, or how hard it is to get something to start moving, or how hard it is to get something to stop spinning, or how hard it is to stop it from spinning, right? It's all those things. So the words are right here. Rewind, listen to this a few times so that you need to, but it's all about how easy or hard it is to start to rotate or to stop rotating, okay? The smaller the inertia, the easier it is to get it going and the easier it is to stop it. The larger the inertia, the harder it is to get it going and the harder it is to stop it. That's the main beans of it there, okay? So when we look at the difference, right, translational motion, rotational motion are different. Again, you've went through torque already. You've talked about rotational motion a ton up to this point, okay? So it's nothing new, right? But we're just kind of applying it a little bit, right? So we know translational motion, and we can follow this dot, right? When we talk about translational motion, it's just moving in one line, right? That dot, no matter how this thing is spinning, whether it's a disc or whatever, we can see that it's moving in this, right? We can track the path in terms of just a linear motion, right? But if we look at just the rotational motion, right? Even though this thing's moving that way, we can just look at how it's spinning, right? And we can track this red mark that I have on here, and as it spins, right, we can see that it goes from here to here, right? And then from here to here, and then from here to here, right? That's how the rotational motion works, right? So for something spinning, not that you don't know this, right? Or for something rolling, right? It's spinning and sliding, right? It's moving this way, right? But it's also spinning as it moves this way, right? So it's combined motion when something spins. And we have combined motion. We like to use a conservation of energy to describe that, like rolling objects. We'll talk about that in a second. But again, what we want to do is, since we do use energy for those problems to solve for objects that are rolling, we got to just remind ourselves what conservation of energy is, right? We know the conservation of energy equation and what should go in there. So we know translational kinetic energy is written as 1/2 mv squared. That'll never change, you know that. The new one we're giving you is rotational kinetic energy, right? Which is 1/2 I omega squared. Okay, 1/2 I omega squared. All right, and so what you'll see here is there's another video that talks about how these can kind of come, how we can get this from this, but the idea is that you have two different types of kinetic energy. So you're going to have two types of kinetic energy in both your initial and your final, right, values in terms of your conservation of energy equation, okay? So that's what's important to remember, where this I value is the inertia. That's how we describe the inertia. Like we said, for linear motion, translational motion, mass is your inertia. So you could write that as I, but we don't, write it as mass, right? But here, the rotational inertia, it's a little bit more. It's this thing called beta times the mass and the radius of the object squared. That's what I is, right? And omega is just how angular velocity, right? How fast it's spinning, right? So you want to, when you're going to write this out, you want to place that in there, like we kind of did. I'm sorry, down here. You'll see how we kind of replaced that I with 1 beta mr squared. Okay, so you want to make sure that goes in there. But we can see the inertia of these objects is based off of, if they're all the same mass and all the same radius, then the inertia of the objects will be based off their beta, right? So the betas, right, are different for every object, and those betas are really indicative of the inertia. So like we were saying, a hoop has more inertia because the beta is 1 in here, right, if it's the same mass and same radius as an object of the same mass and radius, but a disk would be smaller, right? So disks versus hoops are going to have smaller inertia, or hoops versus discs are going to have larger. So what we're saying here, right? So a hoop has large inertia, hard to stop to spin, hard to stop spinning, right? The disc, right, is going to have small inertia. It's going to be easy to start to spin, and also easy to stop spinning. Okay, that's in terms of its rotational inertia, right? So this thing, right, it might not spin as fast, but it might spin longer because it's harder to spin it, right? This one might spin, the disc might spin faster than the hoop, but it'll be easier to stop it from spinning, right? That's how we try to think about those things, all right? So mathematically, how do we prove it? Because we're just stating things here. We can prove it, right? That's how all things in physics work, right? So let's prove it, and we can kind of do it using these two examples here, all right? So like I said, we start with the conservation of energy equation, and then we want to make sure that each one of those values are represented properly, right? So translational is 1/2 mv squared, rotational is 1/2 I omega squared, and gravitational potential energy is mgh. And we did the same on both sides, okay? So we use this generic equation, right? And we can use it based off the situation we have, right? So what I did for this first one, how fast is the object moving when it gets down here at the end of the ramp? That's really what it's asking, right? Well, I kind of already morphed this equation a little bit, right? Because I can see, oops, I have them backwards, I can see, which isn't going to help much, right? But I don't know why I have these flipped, I'm just noticing, but that's a real quick fix, right? So what we can see is at the beginning I have gravitational potential energy, right? But when I get down to the bottom, all my potential energy will be gone, but I'll have kinetic energy, both translational and rotational, right? So I took this equation, I made, just like we do with any conservation of energy equation, I made the things that are zero, right? So on the initial side, there's no kinetic energy, so these were easy, just leaves me with this. On the final side, there's no more potential energy, so that goes away, just leaving me with that. All right? And then what we do, right, is we kind of play with this equation. Now we turn I into beta mr squared, and since we're looking for v, or instantaneous velocity, we don't know how fast we're moving down here, we're not looking for omega, so we want to turn omega to vr, okay? Now, if they were asking for omega, how fast is this thing spinning at the bottom of this, then you'd want to change this v. Here we're changing this omega to vr squared because we want to know v. But if they wanted to know omega, you could turn that v into omega r, right? And then do the same math that we're doing here and take out omega. We'll probably won't ask you to do that very much in class, but keep in mind you can do that. We can change either this v to omega r, or we can change this omega to vr, or since the omega squared, it's going to be v squared over r squared, right? So since we're looking for v, that's what we do. We turn the omega into the v over r, and just like we said, since it's squared, it's going to be v squared over r squared. So our new equation is 1/2 mv squared plus 1/2 beta mr squared times v squared over r, because that was just the omega, right, is equal to mgh, right? And when we look at this equation, we see that there's masses in every term, so that can cancel, right? All the masses will cancel. And then we see that this r squared and r squared sit right next to it, so they'll cancel as well, right? So when we do all that canceling, the masses and the radiuses, we get this right here, right? This 1/2 v squared plus 1/2 beta v squared equals gh, right? Now again, we're looking for how fast the thing's moving, so we need to collect like terms and get v on its own. So the first thing we do is we factor 1/2 v out, because it's in both terms on this side, right? Leaving just 1 plus beta inside the parentheses, and this will still be equal to gh. The next thing we do is we bring that 1 plus beta underneath the gh, right? And bring that 2 up to the top from 1/2, leaving just v squared by itself over here, and these terms on the other side. And then since it's v squared, it's just as easy as doing the square root of all that. So the velocity at the bottom here, right, as we can see, isn't based how large, right? The radius canceled. Doesn't matter how large it is. It isn't based off the mass, because the mass canceled. What matters? How fast it's moving down here is going to be based off the beta, right? We know smaller numbers at the bottom mean larger numbers here. We know larger numbers at the bottom mean smaller numbers here. So we said that the disc should move faster than the hoop, right? It's easier to start to spin, so it's going to spin faster, right? It's harder to get this thing spinning more or less spinning super fast. Is that true though? Well, beta, right? It's going to determine that. The disc is small. There's a small beta, so that means yes, the velocity will be larger for the disc, right? When it gets down here, the disc will spin faster than the hoop because it's easier to get it rolling. By the time they have the same displacement, the hoop won't be spinning as fast as the disc. The disc will be spinning way faster because it has a smaller inertia and it can spin faster. It moves easier, right? But we can see mathematically how that's true. Or we put the larger beta in there, the hoop, right? That's going to be a smaller velocity compared to the 1/2 in there for beta, right? Which means that the velocity will be smaller, right? It's hard. This thing is harder to get to move, so it can't spin as fast by the time it gets down here because it's harder to get to spin. Because if it's larger inertia, right? So we said this, the hoop's going to have a larger inertia, so it's going to be hard to spin, right? So it's not going to move as fast, right? We said the disc is going to be easier to spin, so it's going to move faster. And we see that mathematically is true. All right, so let's see about how high something goes, how hard it is to stop something to move, right? Because the harder it is to stop it to move, the higher it's going to go up this ramp, right? The harder it is to stop to move, the higher it's going to go. So let's see how that works, all right? So the same thing that we did. Start with this basic equation, but we got to start with our situation, right? So initially, I'm spinning and moving linearly. So I have both translational kinetic energy and rotational kinetic energy at the beginning. And then once I reach a certain height, no matter where it's at up here, I'm going to have potential energy. I'll be stopped, so I won't have any more kinetic energy, rotational or translational. So on this side, they'll all be gone, right? So I have this equation. And what you should see is what? These equations that we started with to do this work, they're the same. Do you see that? This equation and this equation, they're the same one. They're just reversed, right? Here it's the initial, here it's the final. It's the same equation. Okay? That's something to point out. I think you should notice that. Okay? But what we do is we're trying to solve for how high this thing's going, so this math's a little bit easier, right? But we do the same thing, okay? We assume that we were just given velocity here. If we were given omega, then we would change this v to omega. But we're going to say, the problem gave us velocity. It told us how fast we were moving down here. So that means we want to change omega to v instead of changing this v to omega. Because again, what we did up with this stuff, you can do down here if you want to. So we extend this out, right? We turn I into beta mr squared, omega into v squared over r. We have our full equation, and just like up here, we canceled out the r's, canceled out the m's, and we get this equation. So again, another highlight here is this equation and this equation. They're the same equation, okay? Except here we're solving this for height. This one we solve for velocity. This is way easier to solve for height, right? So what we do, we kind of do a bunch of steps at once. We divide by g and factor out v squared 1/2, right? And when we do that, that 2 stays on the bottom from the 1/2. It'll multiply by the g that came down underneath this. And v squared will stay up there. And then when we factor out the v squared, this term will be left with just 1. And this will be left with the beta, all right? So again, 1/2 v squared we're factoring out of here, just like we did up here. It's just with this one, that 2 stays on the bottom. That 1's still there. We're just saying it's not, right? So this is the 1/2 right there. It's there, but we're not calling it 1/2. We're just saying, hey, times 2. Okay, it's easier to see that way. Okay, we can just multiply it by 2. Sorry, I want this to look nice for you. Okay, because that's just what that 1/2's doing. And then the v squared and the 1 plus beta stay on top. So the height, right, is going to now determine, now beta has a direct relationship with height, which means the larger the beta, the higher it's going to go, right? The smaller the beta, it won't go as high, right? And why is that? Because we said smaller, the betas determine inertia, so the smaller beta, smaller inertia, the easier it is to stop. It won't go as high because it's easy to stop. The larger the inertia, the larger the beta, it's going to be harder to stop, so it's going to move higher on the ramp. Okay, we know this to be true because of what we know about inertia, but we see it mathematically right here. Okay, I'm going to warn you. Do not, as you know with any physics, you don't memorize this and you don't memorize this equation. Memorizing doesn't help. You should know the work and how to get there and why we did what we did, because these can change. This might not be the answer. What if you have to change things to omega? All the velocities are omega. I didn't do that here, but it's the same work. You should be able to do it. Just instead of changing omega, you're going to go through and change the v. All right, so keep that in mind. No memorizing. Know what we did here in the steps, and I just explained it to you. You should know. All right, so what if we have something a little bit different? Not something rolling, but we still have some rotational motion combined with linear motion, like on a, right, like this elevator, right? This elevator moves up and down. But this pulley, right, ravels up the rope or unravels the rope that's attached to their cable, that's attached to the elevator, right? So we were just given some situation, random situation. We're saying that this elevator is moving down. We know because that's the acceleration. I guess the velocity should be on here too. But that's the acceleration, okay? So we know it's moving down because of the information we're given, right? But how do we put... Because this system is combined. This is all one system. So how do I connect the linear motion to the rotation? It's not that difficult. So rotational motion, as you've learned, because you've talked about torque already, can be described by torque. Okay? Can be described by torque. And we know that torque, right, in terms of Newton's second law, and we know Newton's second law is because since we're moving down, right, and this is telling us we have acceleration in the same direction that we're moving, so that means we're speeding up, right? We don't have to be told, that means we're speeding up. If we're speeding up, we know there's a change in motion. If there's a change in motion here, there's also a change in motion in the hoop, the unraveling, which is described by alpha, right? So linear acceleration is A, rotational acceleration is alpha, right? So we can write Newton's second law, right? Because torque can be written equal to 0 or written to I alpha if we have change in motion in terms of rotation. That's what we do here, right? And we know torque is written, you know, when the force is perpendicular to the lever arm or to the radius, right? We know that torque is just written force times the radius. So we can write a general equation where the torque is going to be written force times r, and then on the other side of the equal sign, we make it equal to I alpha because it's Newton's second law in terms of that, because we know there's change in motion. Then we can put those things together, but this force becomes tension, right? This tension is the force that's applied to this hoop, right? Or this thing that's unraveling. So the force is tension. The radius is just the distance from the axis of rotation to the tension, which would be the full radius of that, right? And that'll be equal to I. Now we can write it two ways. If they tell you inertia, it's a certain value, right? Then you can just use this, right? And you can solve for alpha, or if you know alpha, you can solve for tension. You can solve for anything in there now, right? Just know it can be written two ways. Sometimes you won't be directly given inertia, right? Sometimes you'll have to turn inertia still to beta mr squared. Then you'll look at this as a disk or a hoop or whatever, and that'll change your beta, right? And don't forget to keep it multiplied by that alpha there. That's not a subscript. That's the acceleration, right? The angular acceleration, right? So there's your full equation, either one, right? That's describing the rotation part up here. Now what about what the elevator's doing, right? Well, it's just moving up and down, but it is speeding up, right, as it moves down. Well, that's a lot more easier, right? It's Newton's second law. It's moving down in terms of our coordinate system, and we're assuming down is negative. Okay, we can write our equation. Tension's up, so that's positive, right? Minus mg, which is down. And then this is going to be equal to negative ma, because acceleration is also negative, right? Now you have two equations, and you can put them together. How? What value do these equations share? Tension, right? I can solve this one for tension, or I can solve this one for tension. It's all up to you. So let's just solve this one for tension, okay? Tension is equal to, what? Mg minus ma, right? So this is going to add over, and that keeps it negative. And then if we got to combine these two systems, if they want to know, like, the alpha, right? And you don't know the tension, you can use that tension in there, right? So you can put that tension, that mg minus ma, this is going to go in there. This will all be times r, right? And then equal to I alpha. Or if you write it the long way, it can be written mg ma r is equal to beta mr squared alpha. Okay? So this is two ways to combine linear motion and rotational motion, okay? I showed you rolling objects and I showed you a system, Okay, so make sure that you're able to combine these things because it's important that you're able to use it all. Don't forget what inertia is. It's super easy to remember, and it helps so much because it helps you determine things and helps you answer questions conceptually, right? Super proud of you. Keep up the good work because you're doing it. Even if you're sitting there saying, I don't know what's going on in physics, it's hard. You're trying. If you don't give yourself credit for trying, then what's it all about, right? It's when you put in effort, that's huge. We don't give ourselves enough credit for just giving effort. We're so worried about the result. But it's the effort that's key. And it's the effort that makes me proud of you. Okay? Proud of you? Keep up the good work. See you in the next video.